Nick.
Alrighty, am I viewable in presentation mode for my slideshow?
That works. Yeah.
Alrighty, yeah, so like Alex said, I'm going to go over our systems experiences, especially with respect to what the mechanics of running a system look like at LANL, and then hopefully if I have enough time, I will run a downtime on a system. It's one of our test systems downstairs in the USRC, so it's not the exact process I'll be describing, but it should get the idea across. So this is what I'm going to go over, our systems, the artifacts that make those systems in a hopefully pretty complete sense, like everything that we put into a system, the advantages of doing that, and then where we're looking at for next steps. So I think we kind of covered this already earlier in the week. This is our systems overview. We've got a 4-node HGX cluster, an 8-node HGX cluster that should be somewhere around like 20 to 30, I think, in a month or two here. A 15-node consumer server system. So this is like a potato head style setup where it's got, I think, 4 different blade types in it or something like that. It's currently being used to onboard a visualization cluster. So we're, testing graphics forwarding and how to hook it up to 3D projectors, things like that. And then a 600-node consumer blade system that we've used for scaling that is slowly dying because the hardware is pretty old. Importantly, the artifacts that go into a system, so we've got our OpenCHAMI stack, right? So there's the container images that go into that. There's the cluster images, so the squash FS files that you convert into either an NFS mount or you live mount onto a running system. There's like 7 total image types there, depending how you skin it, but many intermediate layers that make those up. There's the system node layout. So your SMD and BSS data, I consider an artifact, right? What are your nodes? What are their MAC addresses? What are their host names? Things like that. And then our Cloud Init configuration, which is at the moment 1,400-ish lines of config management, including templating. So that's including your file content, right? So if we're templating out an SSHD config, it includes that SSHD config. So it's inventory plus config management. So these are our system images. So it's, pretty simple, right? So we've got our IO nodes that do the routing, our subnet manager nodes that configure InfiniBand switches, our Slurm kettle node that does scheduling, and then 2 flavors of front end and compute. That's really all we've used so far. We use Cloud Init for personalization, right? So if you've got a GPU-less compute blade, the idea is that a compute image should cover every single one of your cluster types. And if you need something more specific, you should try to put it in Cloud Init for personalization first before putting it in the image. And if you can, it should go in the image to be common across the environment. Our system node layout. So importantly, our current hardware is either too simply laid out or too old for strong redfish discovery, i.e. Magellan. So we've been using static node layout files. This gets populated to SMD via Ansible, and it just calls the OCHAMI command line tool. So it's literally like OCHAMI SMD put -d, and then you provided a payload. And this has been scaling okay for 600 pretty static nodes. I think for 6,000 or so nodes, we need to think about Magellan for system lifecycle management, especially, so as nodes flow in and out of the cluster. Cloud Init. So Cloud Init's another core piece of this, right? It's very, very fast. It's like 35 seconds or something like that for configuration. It's very widely scalable in the sense that you're just serving a web page, literally. It's extremely kind to systemd. This has been a very big change as far as like the culture of how we run downtimes and expect our systems to behave. So it integrates with targets early on in system boot. I'll show this later, but Cloud Init's very early on in your systemd targets. So before you're starting SSHD, Cloud Init is configuring it, things like that. So you don't sit there and have services flail. So that's been really nice. It's harder to troubleshoot though, not impossible, but Canonical definitely cares less about their logging stack than Ansible does. So it's, not impossible, but there's definitely a learning curve to figure out, something has gone wrong. How do I figure out what has gone wrong? Systemd also has fun ideas of what a working system means when it works with Cloud Init. If you run Cloud Init and it doesn't break a systemd service, systemd considers that a completed successful run. So if you have things misconfigured, Cloud Init may say it succeeded. And then figuring out how to put things in the image versus Cloud Init, I think is a pretty heavy strategy decision. There's no right answer, right? So a lot of cloud providers provide a very basic image and then do a ton in Cloud Init. And then some other cloud providers do a lot of personalization in the image and have a bunch of image types. I don't think there's a right answer here. It's just culturally, where do you want to put your work, right? Do you want to be churning images often? Do you want the flexibility of having a bunch of stuff in cloud in it with the additional work and troubleshooting? I don't think there's really a right answer, but it is a place of choice, right? So moving on to advantages from artifacts, right? So all of these things mean that human time to change is pretty good. I think this is because we're restricting our configuration pathways, right? So if you want to change what's running on the cluster, you really have two choices unless it's somehow coming directly from an OCHAMI service. So you either change Cloud Init or your image, and that's pretty much what you do. You load an image, you boot an image, and you run Cloud Init on it. We've been automating wherever possible. So this means image builds at the moment. So every single commit to an open merge request that affects an image builds an image. Which has been really helpful, right? If a bunch of work happens in your image and you see a failure, then it's really easy to run ahead of your failures before your DST day. We also experimented with automation of artifact deployment, but I think that's a pretty big piece of work to automatically change cluster state, right? So think changing Cloud Init and cycling the cluster like a DST style with automation. I think it's where we want to end up, but it's also a big risk center. We're able to separate out our image build, artifact deployment, and cluster downtime, right? So each one of those represents a stopping point. So often our image build is done the week before a DST, our artifacts are deployed the day before a DST, and then the cluster downtime is quite literally just rebooting and checking state, which lets us have the users see a lot less system downtime, like in the scale of an hour, hour and a half, and that includes code testing. Our actions for all of these things are standardized, right? So deploying an image, deploying a Cloud Init config never really changes, which really helps shape what your downtimes look like. If you're thinking how to onboard people, it means that running a downtime is now a very standardized thing, right? It's just switching out an image, switching out what you point to, and then you move on. And then system time to cycle state, like I said, building artifacts beforehand lets you build confidence. Teeing these changes up also lets you build confidence. You don't have any surprise, oops, we messed up the inventory and are trying to imply invalid groups or anything like that. And then system cycle is very fast. I think that's, yeah, system cycling speed is my next piece here. Our service requirements are really simple, right? So you DHCP, you load an image, it's chain load because it's PXE chain loading, and then you Cloud Init. Since we respect systemd, there's no like uptime flailing where things fail and then have to kind of sort themselves out by upping and downing randomly. And then we're trying to kexec in many places. Kexec's kind of a newer workflow in my mind, newer being like 5-6 years old, I think, which importantly avoids posting, so we never actually power off the system. So that, depending on your hardware, can make a pretty big difference, right? So posting on an H100 does a memory check on every card, which takes like 3 or 4 minutes per card or something like that. In best cases, we're schedulable 1.5 minutes from post. So that means that Slurm is up, Slurm is ready, everything is config managed. Like we have no changes to make. And that's 1 minute from kernel, right? So the moment we switch root into kernel, that's where we get I think this, yeah. So this is our boot record. So systemd analyze shows you where you spend your time booting up, right? So you can see it took us 7 seconds in kernel, 40 seconds in RD, and 53-ish seconds in user space. So a minute 40 here. So a bit longer than that 75 seconds, but you can see we only spent 53 seconds in user space there. And for a detailed breakdown, you can see why, right? So this is critical chain. Critical chain shows the like worst case scenario of your final target dependencies. So systemd is pretty parallel. So this isn't catching all of the side things that happen. It's just catching the worst case step on the way to each target. And you can see that most of these things are like sub-second, and we've got a few like 5 to 10 second things. And then Cloud Init, our config management takes 34 seconds. So that's a place to look at stuff. And Network Manager, I can tell you that Network Manager, depending how you configure it, will try to DHCP some interfaces politely, even though it doesn't need to because it already has IPs. So that's kind of a config management problem. But overall, you can see, right, 53 seconds, and then this plus like the pivot route. So when you're in slice, this is, I think, before your pivot route over to your main kernel. So there's a bit of time down below this, right, before we're tracking there. But point being, we're talking like time scale of a minute, right? Our legacy systems look like this. So they are 20 minutes, and you can see there's quite a bit in user space, right? So that's our time running things like Ansible. So when we say Ansible spendy, it's because it takes 10 minutes to run like a few tasks. It's just got spin up, spin down time. It's the cost of doing that. I think there's some HPE-isms here too with like the Wicked service and things like that. But really most of it is Ansible. Ansible spendy. So not running it has been very fast. What else do I have here? Next steps. Yeah, so our next steps are how do we scale? These are pretty objective measurements. So you can use eBPF to objectively see how much NFS is serving out. So I can tell you that we load like 540 megabytes on our 6.5 gigabyte HGX image to boot the node, right? Like objectively, you send out 540 megs of data to boot a node. Cloud init's about 10 kilobytes. This scales with how much you put in your cloud init. Ours is 1,000 dish lines, and if you WC-C it's about 10K characters, something like that. And then DHCP is pretty wildly cheap. It's hundreds of bytes, but it's early on and sensitive in the boot process. So thinking how we scale each of these individually as problems is important. But I think the most important thing is nothing is stopping us from a sharded setup where we have multiple head nodes, multiple OpenCHAMI setups, or we deploy multiple DHCP servers and do helpers, or we put the image server somewhere else, right? So we're serving images from the head node right now, and it's just NFS. You could do S3, whatever, right? So nothing's stopping us from taking our scalars here and scaling them individually. And then how can we go faster? So system stage is so fast that now we're worried about things like how does our init-RD look? Are we DHCPing multiple times in our init-RD? Are we sitting waiting for interfaces to try to come up that will then, stop trying, which normally wouldn't be a big portion of your boot, but if it's 20 seconds on a minute and a half now, it's an okay portion. Formalizing what a system DST looks like. So this is what I was mentioning earlier, right? If your DSTs look very standard, where you say, we change out our image, we change out our inventory, we change out our cloud init, that becomes a very easy early employee onboarding step. And then aiming for out-of-band upgrades. So this is what Alex was talking about 2 days ago or something like that, right? Can we do our upgrades automatically? Our DSTs right now, morning of, are literally typing reboot or scheduling a reboot. And it tends to work pretty good. So how can we make that normal, and how can we formalize process around that and testing around that so it's safer? And then deploying more systems. So we're looking to replace our CSM system stacks. There's fun in there, like how do we do Slingshot and run the Fabric Manager, things like that. And then visualization clusters is our actual next deliverable in around December. I think that is it for there. I'm going to pause for like 30 seconds to see if we have any questions, and then I will set up for running a downtime.
All right, I've got a
Nick.
microphone. Anyone have any questions?
Jeff's.
Okay.
Yeah, just
Yep, we've got a question. over here.
Jeff Ogden at Sandia. Question about where do you guys stick the programming environment bloat? Is that packed into your?
So I have a good answer and a bad answer, I guess. So for our HGX clusters, we shove them in containers, which is us saying it's not our problem. And then for our Cray systems right now, the programming environment is decoupled from the image and lives in NFS. So they do like a SPAC build of everything, and it is related to the running image, and that running image is currently built by OpenCHAMI. So we're prepared for the like real programming environment problem, but currently containers and machine learning workflows make it really easy.
Okay, thank you.
All right. So for the kexec boot, does that actually allow you to like fully rerun the kernel boot line? Like you're able to actually load a new image through that, or Or you
Yes, so I will demonstrate that with this DST. I will update our image and our cloud init, and I will kexec. The kexec in our test environment's a little slower. It'll take like 3 minutes because it spends 1.5 minutes in its initRD DHCPing or something like that. But it's still pretty darn fast.
So Nick, I'm going to see if there's any other questions here in the room. Okay. Cool. Looking forward to watching a DST.
Yeah. Oh yeah, this is. So we have our entire stack running here, right? So you can see there's a few extra things running. I'm trying to think of any easy extra callouts. Probably the Kickstart server, things like that, right? So we're running next to a few other services, but the core OpenCHAMI stack is running here. Like Alex mentioned also, choose your own auth adventure. So we just have a local auth server. So that's what Hydra, Opal, etc. are here. Let's see if it works. There we go. So I have an access token to talk to my APIs. So I have an OpenCHAMI command line, right? So that's how I'll be doing that. I'll show off the artifacts first thing, right? So when I say artifacts, I really do mean like things that are sitting in a place, right? So we have a file that is diffable that describes all of our nodes. There's 3, 4, 5, 6 nodes here. So it's not a big cluster, but it does have like, this can go in config management. You can literally diff. So if you're swapping blades, it's not that bad to, show the history of what has X3000, C0, S0, B3, N0, or NID forward been doing. Like how many times have we replaced it? That's a very trackable thing. As are your image mappings. So let's do, yeah, we can do images. I'll do the one I'm actually using, Rocky Base. So this is the image build tool stuff, right? So this is also a very trackable thing, and it's just a YAML file for config. So it's the exact same stuff you saw in the tutorial if you went to that. I think if there's any other good things, I can show off Cloud Init. Again, Cloud Init's a little harder, right? So we can see that there is a Cloud Init group. So groups get applied to SMD groups is kind of how it works. So this is what's going to let me in as root. So this is the config for the authorized keys. And then I have Cloud Init CI group blue. And then I have one that will write blue to Etsy color and one that will write green to Etsy color. So I'm going to be updating from blue to green during this, along with doing an image update. Let me see if I've got anything else there. I don't really think so. So here you can see my boot parameters, right? So this is showing. Oh, yep. Go ahead.
The far right of your screen is cut off just a little bit. Is there any way you can move it a little bit?
Is that it?
Far
Does
left.
that do it? Oh, far left. Oh no. Does that do it? I can try resharing. Let me see if I can reshare through Zoom, or I can just share my whole screen, but I presume that'll be share a window, share this window. Is that any better?
That is better. Thank you.
Awesome. Okay. All right, so I'll start here again. Yeah, so here's my boot parameters, right? So this is what says, here are what Macs get, what initRD, kernel, and parameters, right? So this is kind of how you do an image update, in the sense that if you have a new image sitting where you want your images to be, in this case, they're S3, you could point to where they go, right? So you can see we have a live image here, and it points to this IP, which is our IP, port 9000, boot images, compute, base, Rocky compute, base 9.5. Let's see where I'm at on this. Yeah, so data S3. So we're just storing it in S3. So we can see boot images, compute, base. So you can see we've got 3 images here. I'm going to be swapping from what we have now, which is compute base, to compute debug. So that'll be my image side on top of my Cloud Init side. So I'm going to kind of cheat here and copy my giant BSS boot params command, and then it'll show off what that did. So this says update my boot parameters with a YAML file, and it says compute debug. So if I cat this, you can see what it's updating to. So you can see here, all it did was change from compute base to compute debug. So I've changed an image. This could be in, like a more real DST, a major OS update, or switching your OS, or switching your image. In most of our cases, it's just a minor revision on our images, which does involve like a kernel update. But by doing this command, I've now mapped a new image. It's like one command, one file. In production, we manage this with Ansible, but it is literally the same thing where we're dropping a YAML file and calling OpenCHAMI BSS boot params update on it. So now to move to CloudInit. So here we've got CloudInit group get config. So this gets all of the configs for all of the groups. And you can see we have a blue group and we have a green group. So those are our configs we will be mapping. So we're going to join nodes to these groups pretty much. And then everything's in this compute group that gets its SSH authorized keys. So if I do an OpenCHAMI SMD group member get blue, you can see everything's in the blue group. And if I do a get green, you can see nothing's in the green group. So I'm going to delete everything from the blue group with the giant xargs command. So the OpenCHAMI command line doesn't do great at like active group membership like this. And that's, I think, because that's not something you'd be doing that often. Normally, we'd just be updating this blue or green group. I just wanted to show a change between though. So this just says, get all of those components just like I did, and then get their IDs and feed it right back into delete them from the group. And then I will be adding them to the green group, which is much the same, right? Instead of saying delete, I say add. And now if I do group member get green, you can see I have X names there. And if I do group member get blue, I do not. So I have changed what groups I'm in. I've updated my image so I can move to doing the DST. So I'll SSH to a node. This is about to be a giant brick of bash. If anybody wants to hire my last student, please do. He's the one that wrote this. So what this is doing is it is getting your NID, your MAC, etc., from your command line, and it is then getting from BSS our next targets, right? So we don't have to know what we're going to. We can just have every node ask BSS, hey, what will I be doing? And that sets a few things that are important, right? So our kernel and our initRD. And I'll break this into different pieces once I run this too. From here onwards, right? So this curl, so we grab our kernel, we're literally curling it into a temp directory. So if I do ls temp, you can see I've got my new initRD and kernel, and then you can see I've kexec loaded that. So I loaded my kernel and initRD and my command line. So at this point, I've got all my new stuff loaded. So upside, this is done live and we're ready. Downside, I've now eaten, however much data temp is into RAM, right? So 87 megs, not too bad. But I have changed system state in the sense that I've eaten a little bit of RAM. And then doing a kexec changes your reboot target. So I will type this quick because I don't want to do a tmux and clutter space, and then I will look for showing what our kexec actually looks like. If I can find it, it might already be due. Oh no, here we go. System D. I might not find it quick enough. I should scroll to the bottom in a sec here. Yeah, I probably missed it. But you can see we're already back in the kernel. Somewhere here it should say, welcome to Rocky Linux. So that's how long it took us to return to init ramfs. So we never actually, posted. So it's like 10 seconds and we're back in it. And then here's that, we are now waiting for, I think this is network D and defmapper or something like that. But at this point, I've done all of the hard parts for a DST, so I can pause for questions for 3 minutes while this goes.
All right. Are there Are there questions in the room? So I have a question, comment. So I know that at one point when we were looking at this, there was, instead of having to do all of the things that you just did with the scripts and the awk and all that stuff, there was a system D target that we were able to use
Yes.
that sped that up. So are we still using that, or was that not?
That exists in the prod that is harder for me to screen share and not the USRC basement. So yeah, so in prod we can literally do like, it's like system kettle start kexec or something like that, and it will prep everything. So yeah, that exists over there, and as well in BSS, we have an option now to do JSON as an output instead of just straight up your command line, which lets you grab things with JQ instead of doing weird greps. So it is much more pleasant in some places, yeah. And we've started using kexec more often over there. We've had hardware maintenances recently, so I'd say it's probably been like a month since we have, but that's just the way it goes. And then here again, you can see there's another network manager wait, so this will take about a minute. But these are all things that you can like tune, right? You can configure network manager to not do this. You just actually have to provide it configs to do so.
A question about when you talked about scaling up BSS, you mentioned you're using 600 nodes now. Would a scale up situation be that you have a BSS for each group, or is it a more dynamic sort of setup?
Storing data in BSS is not expensive, so I presume what we would do is load BSS with every node and then have the nodes reach out to different BSS endpoints or put a load balancer or something like that in front of it. So DST's done, so that's pretty quick. Uptime, it took 3 minutes from getting kernel, so that's not too bad. And if I do system D analyze critical chain, you can see, from slice to graphical target was 1 minute 6 seconds. So yeah, I think BSS, not too worried about scaling. DHCP is a little harder since by definition it sends broadcast packets, so you're configuring switches and kind of doing a little bit of finicky layout. Images, even harder. My hope for images is that we can point it to like a beefy local PNFS kind of thing, but I'm not sure. I think S3 is also probably pretty good. But I suspect since that's like 2 magnitudes of scale increase or 3 or whatever, that might be the place we run into a little bit of pain comparably to the rest. I'm not
Sure,
too
just
scared.
in hosting those multi-gigabyte or 100 gigabyte images.
Yeah, and if you think about, the 500 megs loaded in our scale of 6,000 times, that's like 3 terabytes, right? Every boot, which isn't a horrifying number. Our users pull things bigger than 3 terabytes regularly for their jobs, but it is something that you have to think about what it looks like coming from, 6,000 individual hosts tightly coupled. So it's a scaling concern.
Absolutely.
Probably the biggest one.
Hey, Nick.
Cool. Thanks, Nick. This is great.
Yep.
Hey, Nick, didn't you do some characterization of how many bits are actually coming across versus the size of the image at one point?
Yeah. So
it's not the whole thing.
yeah, I used eBPF to very objectively measure what we actually call NFS read on, and it is only like 540 megs for our GPU images out of 6.5 gigs. And I would suspect that number doesn't really increase, right? Linux doesn't magically read more files because your image is bigger. So until your users or your workflows or whatever actually start calling LDD or whatever on your files, right? I suspect you're talking like 500 megs-ish per node, no matter image size.
Cool. Other questions in the room? Go ahead.
No, I was just going to ask about more about the scaling. If you, some of the ideas to, obviously have a top level OpenCHAMI node and then boot a mid level and then have it, is that kind of what you're moving towards, mid level of image and BSS servers?
Alex had a name for this and I forget it. That's something we've debated. I don't want to like over jump into we want to do this architecture until we run into a failure case, if that makes sense. So I'd want to measure first.
Okay,
And I
yeah,
do think a lot of
completely.
these things are super measurable. But yeah, I think a mid-level service architecture is one very easy way to do it, right? If I had to boot Crossroads in 3 weeks, that is what I would choose to do. I would stand up 3 OpenCHAMI instances and split the cluster in thirds and set the DHCP helpers to do stuff like that. So that's what I would do if I had to right now. Yeah.
Yeah. This is Alan. We got a couple more questions in the room. I'll just follow up to that, that when I did, because of the way BSS works, it loads everything into memory. So it's not hitting a database every time, which means that all you're ever really doing is pulling that, 10 kilobytes out of memory and sending it down the wire. We should be able to do certainly thousands of concurrent BSS requests without trouble. There's, network contention issues around other things, but I don't want to do premature optimization for the idea that we might need this until we have some evidence that we actually do.
So my question is more around the performance. Have you tried installing a large compute base, and have you run into any bottlenecks, and what you did about it?
So our largest image is 6.5 gigs, and we haven't had any bottlenecks so far. So yeah, again though, I think that could change if you have workflows that are very image heavy, right? And they hit in a very parallel fashion where all of a sudden you're trying to load 3T. I think it's just a question of whether your image server can handle that, right? Here at least, I think that our bigger burden tends to be the data sets that people are pulling, but we've also designed those file systems to handle that, right? So those just have had a closer eye on them. So my probably mediocre answer is no, but I think we can design for it.
And just, I'll follow up, going back to what you said before. When you look at the actual NFS traffic for a boot, even if the image is 6.5 gigs or even 100 gigs, you're really only looking at 500 megs.
Yeah,
Right.
yep. Until you
And
start actually touching system space for
until you actually
libraries.
start getting into system space,
Yeah.
your size of your remote image doesn't really change the boot time.
Yeah, and I can go find the BPF script stuff I used and post that in the Slack too if people ever want to measure locally. It's not too bad. It just measures every read and gives you the buffer size.
Other questions in the room? Anyone else online?
Alrighty.
All right, thanks a lot, Nick.
Yeah, thanks guys.
Slides, or is this